I do welcome all of you who have managed to tune in and have this conversation with me in mathematics for economics, and we are looking at the unit partial derivatives, higher order derivatives, and total differentials. So, what is it that we want to conversate on? To put a background to this conversation, if you do remember, and we were looking at lower order differentials. We looked at the functions that dealt with only two variables, one dependent variable and one independent variable. You could have functions such as the function of f of x is equal to 3x squared plus 5x, just like that. So, or you could say y is equal to 3x plus 5. So there would always be only one variable on the right hand side of the equation. But this time around, we want to ask another question. What if now, instead of having only one variable, the other side of the equation, you do have many other variables. Maybe you have three variables. Maybe you have two variables. For example, you have maybe 3xy plus 5xz plus 6. How do you differentiate such functions? So basically, that's what we want to conversate on. And we are now starting the conversation. To be actually much more realistic in economics, we assume an economic variable that it is just a function of a number of basically different, factors. Remember, there are so many macro and microeconomic variables that we discuss in economics, right? And when we're trying to draw the relationship between these or among these variables in what is known as, functioning, we bring in several variables and draw the relationships within them. Now, the time when you have more than two variables interacting, you're probably most likely to have what we call uh, partial fraction or partial derivatives. Yeah, to differentiate such kind of functions where you have more than two variables interacting, or many variables, several different variables. Let's say y is made up of 3xy plus 2x xw plus w squared, then even plus 2z. Such kind of function is said to contain different variables on the right hand side. The question of the day is, how do you actually differentiate such functions? Yeah. For example, the demand function, we know that it's made up of different functions. There are factors, right? There's so many factors that affect demand. And now these factors that affect demand can be, their relationship actually can be put mathematically, right? We can use mathematics to draw the relationships among these variables. So we shall say the quantity demanded shall be the function of the price and the income of the quantity demanded. But we know there are other factors that affect the demand. So mathematically, this is the relationship for the quantity demanded. We're saying demand is determined by, meaning quantity demanded, right? Quantity demanded Q2 is a function, meaning it's determined by price. It is determined by income, Y for income. It is determined maybe by prices of the related good. Let me put a PR. It is determined by expectations. Let me just put maybe superscript X like that. It is determined by all the factors are put in here. So basically, this is the relationship that we're saying this left-hand side, is determined by the right-hand side or by the interaction of the variables on the right-hand side. Having spoke that now, we could even now bring this to practice and say the output of a firm usually depends on inputs into production process. Yeah, there are these inputs. For example, now you want to see the output of the change. Mathematically, you can say the output, whatever you produce as firm, is dependent on capital and what and labor, the interaction of these inputs that you use, plus many other inputs. So this is what we mean, and this is the idea behind these functions. Now, what do we mean by having these partial derivatives? If we have a function of more than one variable, right? Let's have a function. The function is made up of x and y. That shall equal x to the third degree plus 4xy plus 5 and y squared. This is a function. It has more than one variable, more than one letter in the layman's language. We can ask, for example, how this function changes, right? When x increases, but y does not change. So in other words, we want to ask ourselves the question, what happens to the output in this case when there is a change in this particular variable holding other factors or other variables constant? Okay, that's the message we are sending. So to answer such a question, you need to differentiate the function with respect to that particular variable. So if we are talking about, we want to see the impact of x. When x changes, what really happens to the entire output? Then at that point, we are differentiating the function with respect to x. So for example, an example shall do better. Let's differentiate this. How do you differentiate this? The partial derivatives for this shall be f of x, y, that is equal to x raised to the third degree plus 4xy plus 5y squared. First of all, we can differentiate this function. Let's call this whole function z, all right? Let's just say z is equal to that so that the whole function is z. We can differentiate this function and say z dx, meaning we're first differentiating it with respect to x. Wherever there is x, you differentiate. Where there is no x, it is treated as a constant. Now listen here. So we'll come here where the x cubed. Using the power rule, we will have 3x and the power reduces by 1, then you have 3x squared, right? Plus, I'm interested on this part for 4xy. We are differentiating this function with respect to, listen carefully, with respect to x. You know that this is equal to 4yx, right? This is still the same because multiplication is commutative. What you're going to do now, you're going to realize that this x is raised to the first degree, to the power 1. And the whole root of this shall be treated as a constant, like as a coefficient, all right? This is going to be treated as a coefficient. And just a minute. Okay. So I was making mention that this is treated as a constant, right? Or as a number. So you just treat this as a number. So this is just as good as saying 5x. We know when you're differentiating 5x, you just get the coefficient. So you remain with only 4y. So here you have 4y. Because x is raised to the power 1, it's going to disappear like that. Okay, that's very important. And then we have plus c. We are differentiating the entire function with respect to what? To x. When you have 5y squared, 5y squared, is a constant in this case because it doesn't have x. So it's regarded as 0, this one. So you shall have 3x squared plus 4y as the partial derivatives of zx, or the function differentiate with respect to x. We're not done finding the answer. We also need to differentiate this function now with respect to y and do dz dy, meaning we're differentiating this function with respect to y. So what we're going to do, we are just differentiating everywhere where there is y. X squared, x cubed doesn't have y, so it shall be treated as a constant to be 0 plus c. Now you have 4xy. I told you that since you're differentiating with respect to y, this will be treated just as a coefficient. Then this is y to the power 1. When you drop the power and everything, you remain with 4x. So it will be just 4x because y is going to disappear. So you have 4x, right? Plus 5y squared, it shall become, drop the power 2 times 10 times 5, that gives you 10 y like that. So this shall be your function, zy, meaning the partial derivative of this particular function with respect to what? Y. So there are two answers there. This one with respect to y, and this one with respect to x. So that's how you deal with partial derivatives. Okay? This is just the face example. Have made mention of the partial derivatives. Now, let's also have another example. Another example, the second example is where we have function of x and y equal to x squared minus xy squared plus y cubed. We're differentiating this z function with respect to x to start with. So say the z dx, where there is x, we differentiate. So it will be equal to 2x. We are dropping the 2 here. Minus, now you have xy squared. I told you that we are differentiating with respect to x. Whatever is not x, this one shall be treated just as a number. So this is as good as y squared x. X to the power 1, drop the power and everything you differentiate, you know that you remain with y squared. So you have minus y squared plus c. Now, since this is y cubed is not, doesn't have x, it will be treated as a constant here. It shall be just as good as 0. So you put 0 there, right? You shall put 0 here, plus 0. So that the partial derivatives, or zx, with respect to the differentiation with respect to x shall be 2x minus y squared. This is how you deal with that, okay? The partial derivative. We can also differentiate this entire function with respect to y. Now, with respect to y, you shall be z dy. Everywhere where there is y. Here, where there is x squared, there is no y, so it shall be treated as a constant. 0. Now, this negative x, the xy squared, we're differentiating with respect to y. So we'll treat this, look at the way how it's treated. This is the xy squared. You treat this as a number, just as you treat it as 3y squared. So it will be, you drop the power 2 times this x, which has been treated as a constant, then y to the power 2 minus 1, which will just be y. So it will be minus 2xy plus, we're differentiating with respect to y cubed derived will be 3y squared. All that. This is a partial derivative now with respect to y. If you had z again, there were z or w, would have again differentiated this entire function with respect to z or with respect to w. Okay, with respect to w. At some point, you will be introduced to the Cobb-Douglas function. The Cobb-Douglas function is one of the well-known functions that we use actually in macroeconomics. Yeah, the Cobb-Douglas function is of the form. This function is a function of labor into capital equal to these constants, alpha, L, beta, right? Capital 1 minus C beta. This is the general form. Now, the question of the day is, what is L? L is labor, stands for labor, K for capital, and F simply means this is a function. So now, if you were to differentiate this particular function, then you have to apply the Cobb-Douglas function, okay? You have to apply the Cobb-Douglas function. So now, you have to apply the partial derivatives on this Cobb-Douglas function. Let's have an example, and you listen carefully to this particular example. Zambia's production in the early years following its independence in 1964 is described by the Cobb-Douglas function. This is a function. It is 30 L to the power 2 all over 3, capital 1/3, right? Where X is actually the number, the units of labor, and Y is the units of capital that were used. So they want you to compute the function of L and the function of K, right? Meaning you do the partial derivatives. You have to do the partial derivatives first with respect to L and also with respect to K. Then you have to find the marginal product of labor and marginal product of capital as expected. So now listen carefully to the way how this is applied. The function is this one. The first thing is to take partial derivatives. The function is that L squared, L2 over 3 is a fraction, capital 1/3. So when you want to differentiate this function first with respect to labor, yeah, it means that this shall be treated as a number I told you. So you have 30, okay. There'll be 30, which is actually a constant. Let me just show you nicely. We are dropping this, we are differentiating this with respect to L. So you drop the power, which is 2 over 3 times the constant 30, all right, L to the power 2 over 3 minus 1, we are following, then capital 1 over 3, right? Capital 1 over 3, because this one is maintained the same line. Only this one has reduced power, the labor one. So when you work out that, you will have this particular function, okay, derived, okay? And what will be the derivation? We know that this 3 into 30 is 10 times 2. It will just give us 20, right? 20 L to the power. What is the 2 over 3 minus 1? So be 2 minus 3 over 3. That will be 1 over 3. Negative, actually. So it will be to the power negative 1 over 3. So L is to the power negative 1 over 3. Capital is 1 over 3. You're following, right? Hope you're following on how you handle the Cobb-Douglas function. This is maintained like that. So from the rule of indices that we did, we said you can simply rewrite this as 20 multiplied by this which has negative. The whole lot of it shall go under the denominator. So you shall capital to the power 1 over 3 divided by labor to the power 1 over 3. Now we know that we can remove the power since they all share the power. It will be 20 multiplied by capital over labor to the power 1 over 3. According to the rule of indices, we know that this 1 over 3 is for both capital and labor. So this is the function. This is how you do it. Okay, you have differentiated. That's how you differentiate the Cobb-Douglas function. Find the marginal product. This is the marginal product of labor, right? Marginal product of labor. If you want to do marginal product of capital, you repeat the same process. Look at it again. You have the function 30L to the power 2 over 3, capital 1 over 3. Then now we are differentiating with respect to capital. So drop the power for capital, which is 1 over 3 multiplied by 30, right? L to the power 2 over 3. This will not be touched because there is one number they are combined together. There is times here. There is no plus. Okay. Capital to the power, 1 over 3 minus 1. It always reduces by 1. So we know that this will give us 1/3 times 30 gives us 10. You have 10 multiplied by, L to the power 2 over 3, K to the power negative 2 over 3. Because when you say 1 over 3, this one, 1 over 3 minus 1, it gives us negative 2 over 3. And at that point, we know that we can still rewrite this. Since K has a negative power, we can bring it under the denominator. So we can have 10, to the power L 2 over 3 divided by K will go under the denominator K over to the power 2 over 3. And we know that they now share the power both. So you have 10 multiplied by, L over K to the power 2 over 3. So basically, that's how you deal with the partial fraction. This one will be the marginal product of what? Capital. Because we are differentiating the production function with respect to what? To capital. So that's how you work out this. Now, the question is still continuing. The question was asking you that what happens now to these marginal products when you're given these units? So let's say we are given this data. We want to find the marginal product when the units of labor where L is 125, then capital is 127. So where there is labor, you put 125, then capital K, you put 27. What will be the marginal product? So we're just going to replace into this, function, these two functions. So the first one is this one, 20 multiplied by capital is what? What is capital? Capital is 27 divided by 125, right? To the power 1 over 3 or 1 cube. How do you deal with this? We all know that we can write this as 20 times this power is for everything. You can say 27 over, to the power 1 over 3 and 125 to the power 1 over 3. And we do know that we can still rewrite this as 20 multiply using the rule of indices as 1 cube of 27 divided by 1 cube of what? 125. 1 cube of 125 simply means a number that you can multiply 3 times to give you 125 and the number you can multiply 3 times to give you 127. So we do know that that particular number would be 427 is 3. You can multiply 3. 3 times 3 to give you 9 times 3, 27. This will be 9. And times this 3, it will be equal to 27. So 3 is multiplied 3 times to give us 27. So on top we have 3, and down we have 5. When 5 is multiplied 3 times, we have 125. Because 5 times 5 is 25. 25 times 5 is 125. So this is how you deal with this. If you want, you can still further simplify this. 5 into 20, like 20 times this, summarize this function. You will have 20 times the 3 is 60 divided by 5, that will be 12. So the marginal product of labor is what? 12. The marginal product of labor is 12 at these points. When labor units are 27 and 125, happy. Okay. Now, what about the marginal product of capital? Then we use this function, the one that we have differentiated, where I say 10 multiplied by L over capital to the power 2 over 3, and substitute. Our labor function, we had that we have 125 units to be divided by 27 units, and all that to the power 2 over 3. And I did indicate that 2 over 3 is same as 10 multiplied by the third root of 125 to the power, okay, 2, this 2, divided by the third root of 27 to the power again 2, that's 2, from the rule of indices. And then when we work out these, what is it that we're going to find? We know that we shall have 10 multiplied by the root of 125 is 5. So, the cube root of 125 is 5. Then we have 5 to the power 2, which is 5 squared. And the cube root of 127 is 3 squared, like that. And we can go further, simplify. So when you simplify further, you shall have 10. 5 squared is 25. And the 3 squared, 9. So you have 10 times 25 over 9, which shall be 250 over 9. This is as good as 250 over 9 units. That is the marginal product of capital. So you need to be very competent indices and work with the indices very well, because now we are getting to the applied level of indices, right? This is applied level of indices and calculus. So basically, this is the same message that we were actually sending. Okay, we were sending this particular message. Yeah, you can still rewrite this number. This is what I was saying. You have 10, 10 multiplied by 25 over 9. You can simplify this further if you may be interested. It will be 250 over 9. If you want, you can write it as a mixed fraction as 7 to the power remainder 7 over 9. Yeah. Okay. So now, this is the function that we have just been given, and at least we have dealt with this, and we are better now. Let's talk about now what you call higher order derivatives. Higher order derivatives are derivatives that have got, the powers that are differentiated more than once. All right, you got to differentiate the same function several times. That is what we mean by higher order derivatives. It's not like the partial derivatives. So, of course, they could be partial derivatives as well, but the message here is that you're differentiating this function 2 times. Differentiate it once, the partial derivative, again differentiate it for the second time. And that is how you deal with the higher order derivatives. So the same function is differentiated 2 times. Okay? Differentiate the same function 2 times. For example, you could have this utility function. The utility function that you have is beta xc, which is to the power alpha, y to the power 1 minus c alpha, right? And we want to differentiate this function with respect first to a, to x. You differentiate this function with respect to x. Now, this is a higher order partial derivatives. We know that x is raised to the power alpha, so drop alpha as usual. So have alpha multiplied by beta. Everything will be treated as constant. Then alpha minus 1 and the y1 minus c minus the same alpha. Okay? That's the same derivative. Now we know that this one has y minus alpha and this one has y minus c minus alpha. Okay, so we could actually, factor out what is common. Okay, we could factor out what is actually common, which is actually 1 over alpha. So when you do your computations, you're going to find that you have alpha beta, right? Y, okay, over x raised to the power 1 minus c alpha. 1 minus c minus alpha. Minus alpha. So this is the partial derivatives. It's the first one. You could also have a utility function that needs to be differentiated with respect to y. This is a utility function. The utility function is differentiated with respect to x, and now we are differentiating with respect to beta. Of course, let's differentiate the utility function one more time. Now with respect to beta, we differentiated it with respect to alpha. Now with respect to beta. How do you deal with it when it is differentiated with respect to beta? You know that, or with respect to y, this is your y. Your y has the power 1 over 1 minus alpha. So you say 1 minus alpha, which is your power, drop the power, keep everything constant, the way how it is, bx to the power a, and y minus c, 1 minus alpha minus 1, which will just be negative alpha. Because 1 and negative 1, they'll cancel, they'll give you 0. So the derivative shall be 1 minus alpha and beta x to the power alpha, y minus y negative alpha. And we could easily rewrite this now. The other one is negative alpha, the other one is just alpha. So we could easily have 1 minus alpha beta, all right? X is positive, shall remain on top. Y has a negative. When it goes down, it shall get a positive sign. So have the power alpha. Because this now alpha is common, has been put like that. This is the first partial derivative. Now, these partial derivatives that you found, this same answer, you could want to differentiate it again further. It can still be differentiated where it is here. Differentiate it again for the second time with respect to alpha, which is here, with respect to x, where x is raised to the power alpha. Again, you can still differentiate it with respect to y, That is raised to the power negative alpha. So that's the message. You're differentiating again for the second time. So differentiate this function. Differentiate this function for the second time. So that's the idea behind higher order derivatives. So higher order derivatives basically refers to the derivatives that differentiated more than once, okay? After differentiating that, we can even go further again, differentiate it for the third time. It will keep on going and going. So this is a second derivative. When you differentiate this function with respect to x for the second time, this one is when you differentiate it with respect to y for the second time, okay? When you differentiate it with respect to y for the second time. Okay. And now there is a problem that I am giving. There is a problem that I need to actually give you. Here is a problem, right? You have a problem to be given. Here is the problem that we have. I want you to work out and find the second order differentials for all these functions. So we have 2x alpha y 1 minus alpha. Please, this is your utility function, x, comma, y. I want you to do two partial derivatives. Differentiate this twice. Find the second partials. You differentiate it first with respect to x and with respect to y, and again differentiate it, that derivative differentiated at first with respect to x. Differentiate it again for the second time, and also differentiate the utility function with respect to y for the second time. So that is what I want you to do so that you can find what we call diminishing marginal utility. So to find diminishing marginal utility, you have to do the second partial derivatives. The second partial derivatives mathematically expresses that relationship that we are conversating on. Okay. Let me just entertain some questions if at all there are any questions. Okay, if there are no questions, we can end here. I have already given the problem to work with. Please handle that problem. Okay, can end here for today. Thank you so much. It's always nice doing business together.